In this notebook, we're going to introduce ourselves to regular expressions, which will become one of the most important tools in your toolbox for working with varieties of biomedical data. As almost any task that we're doing that involves information extraction is likely to rely on regular expressions for extracting that information. Because they're so powerful, it's very fun and the number of things that you can do with them. And as this author of a prior textbook says, you may be amazed at the things that a regular expression can do, but that comes with the caveat that they are very, very tricky. And I almost never try to write a regular expression without having a reference page open to guide me working through the details of regular expressions. So one of the first things I want to emphasize is that when we are working with regular expressions, we define a regular expression using a string, but we always want to use a raw string. And we haven't talked about raw strings before. And a raw string is simply a string that is preceded with the letter R. So right here, this is not a raw string, whereas this is a raw string. And the reason that we need to use raw strings is that a raw string doesn't evaluate special characters in the string. And our regular expressions are going to be built up from a variety of special characters. So let's start off really simply by writing a regular expression to find a fixed string, for example, my name Brian. Now this is something that we could do, and if this is actually the application that we were doing, should do with just a simple string find method, but we're going to start with this for illustration purposes. So the steps involved with using a regular expression are to first import the RE package that is part of this library, that's part of the standard library. Then we define and compile a regular expression, and that creates a regular expression object. And then we will use that regular expression object to find matches within some string. So this cell here illustrates this. So I'm importing RE. I have some string that I'm going to try to extract information from. I'm defining a regular expression here, which is simply the string Brian. Note again that this is a raw string. In this case, I don't have to use a raw string because there's no special characters within the string that I'm trying to match. But in my mind, it's a good habit to just always make a string that you're making regular expression with a raw string. So this variable R1 now holds our regular expression object, and I'm going to use the find all method to find all the matches of my regular expression in name string. And so this will return them in a list. So there was one match to Brian. I can make my regular expression case insensitive with a compilation flag. And so the compilation flag that I would be interested in using in this case is ignore case. And I can either type this out completely, or there's an alias, re.I, that provides the same function. So here I'm just using my regular expression, matching Brian. Here I'm going to match one where ignoring case, and then repeating that, ignoring case. And you can see for the second examples, I get the lowercase Brian as well. Now the real power of regular expressions comes from meta characters that allow us to have variability in the strings that we're going to match. And we won't go over all the meta characters in this, this notebook, but here's a list of all the meta characters. And we'll go over some of the more important, more important sounds a little judgmental, but we'll start exploring some of these meta characters in this notebook, and we'll pick up more in a subsequent notebook. So square brackets are used to specify a character class, which is a set of characters that you wish to match. And there's a variety of ways I can specify these characters. So this example here would match the character A, B, or C. That is equivalent to this meta character where I'm using the A-C. A dash Z will match all lowercase letters, any lowercase letters, and A dash Z and then capital A dash Z will match all alphabetical characters, and here we have all alphabetical characters and digits. So let's see what this looks like in practice. So I have a test string here, which is just my letters, upper and lowercase letters, and the digits, and I'm going to create a regular expression that will match any of the characters in here, A, B, or C. And then if we do a find all, you see that we matched A, B, and C. Here, using the meta characters where I'm specifying the characters with the dash character, you see that I'm matching the same thing. Here, matching all lowercase letters, you see that we did find all of those, and then this will match all the uppercase, lowercase, and digits. So that's a character class. We can specify a character class size by having characters that follow our character class. And so this is where a number of the meta characters come in. So we have an asterisk, which matches 0 or more characters, a plus, which matches 1 or more characters in the character class, a question mark, which matches exactly 1 character in the character class, and this syntax where I have a curly bracket m comma n, which matches at least m characters and at most n characters. And these asterisks plus question marks and the curly brackets can be applied to single characters. They don't have to be applied to a character class. So something to think about: how would you express an asterisk, a plus or a question mark with the m, n syntax in the curly brackets? Well, an asterisk is 0 or more, so I could have a 0, comma, and then leaving it blank would be an indefinite number upper match. And you can work through the plus and the question mark for the others. Okay, so here we have a regular expression where I'm matching the character A, and then that is followed by a character class BCD, which has an asterisk, which means 0 or more of those, and then a B. So I would have an A, 0 or more instances of a B, C, or D, followed by a B. And in this case, I'm compiling it to ignore case. So that's my regular expression object stored in the variable R8. In this regular expression, I am matching an A and saying that I have to match at least one A, but no upper bound is specified, followed by a B. So let's see what these look like. So for the first case, I'm going to take my test string defined above, and let's see, I'm just going to split this, and then I'll do it with the R9. So let's see. So we ignored case, and so with the first one where I'm matching 0 or more, you see that I match A, B in both an uppercase and a lowercase instance with 0 BCDs in between, BCs or Ds in between. With the second one, I need to match an A, at least one A, followed by a B. It's not compiled with ignore case, so I only match this AB. Well, R9, let's get a different string. So an R9 will match an A, at least one A, followed by a B. So let's see what we match here. So we got AAB, so we match 2 A's followed by a B. And here we match the 3 A's followed by a B. Then finally, 1 A followed by a B. Okay, one of the things that will become important as you try to get more subtle regular expressions, that all these regular expressions that we've used are called greedy. That is, the regular expression will match the maximum number of characters as possible that is still consistent with the regular expression. We can define a non-greedy match that will match the minimum number of characters as possible. And the way that we specify a non-greedy match is we have our count followed by a question mark. And so we can have that question mark following an asterisk or a plus. So here's a greedy version of matching the digits with at least 3 and at most 5. And here is the non-greedy version of the same regular expression. So illustrating this here with A's. So here's a regular expression that will match at least 3 A's in a row and at most 5 in a row. And here's the non-greedy version of it. So let's compile these. I'm going to take the greedy version to find all the A's, 3 and 5 A's, in this string of 6 A's. And you see what it matches is a string of 5 A's. Now the non-greedy capture, it will capture the minimum number which matches that regular expression, which would be 3. And so you see we match 3 different three long substrings of A's. And you notice that these are non-overlapping. The matches are non-overlapping. Okay, what if a meta character like an asterisk or a question mark is something that I want to search for? If I put that character in a character class, then they do not have special meaning. That is, they're treated just like any other character to be matched. And there is one exception to that, and that is the caret. So if the caret is the first character in the class, that denotes the complement. That is, it matches all the characters except those denoted in the class. And so here we're defining the character class is A to Z, but the caret precedes it. So this regular expression will match any character that is not an uppercase letter. So let's look at what that matches, and you can see our lowercase letters as well as our digits and some spaces and a new line. The backslash character is used to escape all the meta characters. So to search for an asterisk, we would type a slash asterisk. And to search for a backslash, we would type a backslash backslash. So let's look at this regular expression. And we match the 2 asterisks following F1. If we get rid of our escape, then we get an error, because what this is saying is this is a repeat, match 0 or more, but there is nothing to have this match that we're specifying to match. Okay, now from meta characters per se, there are some combinations. So /D is a symbol that matches any decimal digit. So /D, lowercase d, is equivalent to the character class 0 to 9. And so here I'm just compiling something to match any digit. So that matches all the numbers. I can make this match 1 or more, and I get the 2 full digits out of my string. So /D matches any non-digit, and you'll see this lowercase uppercase complement where the uppercase tends to be the opposite or the complement of the lowercase. So the /D matches any non-digit character, so that's equivalent to this caret 0 to 9 character class. And so let's try this. So here we're matching all these letters and spaces, but no numbers. And we can again do this to capture 1 or more instances of that. So a slash S matches any white space character. So this is like a tab, a new line, a line feed, etc. So the slash S is equivalent to this character class. And you can see us capturing all the character white spaces there. Okay, similarly then, a slash capital S matches any non-white space characters. So the complement of that character class. And we're catching the non-white space strings. Okay, slash W matches any alphanumeric character, so that's equivalent to this A to Z, 0 to 9. And a slash capital W matches any non-alphanumeric character. So that's equivalent to this class. Okay, a vertical bar is an OR, so that says match this or match that. So this regular expression right here will match Wakara or, there's our OR symbol, or Arapine. And so I can use this to pull out addresses in Research Park. So let's put these things together for an actual application of recognizing zip codes. So in this case, we're going to recognize a zip code as being a 5-digit sequence. So 84108, for instance. And I can do this in 2 ways. So here I'm saying match any digit and at least 5 and at most 5. And here I'm using the character class to specify the digits. And in both cases, I'm extracting the 84108. Okay, well, what about telephone numbers? Well, if we think of a telephone number as being an area code followed by the 3-digit prefix and then the 4 digits with dashes in between. So here I'm using a character class for the digits and say I have to match exactly 3 of them. Then I'm matching a dash. Then I'm using the slash D to specify the digits, and I'm going to match exactly 4 of them. And here I have an OR, and now I have an area code, a prefix, and a suffix. So in one case, I'm assuming that there is no area code provided, and in this case, I'm assuming that there is an area code provided. And so let's see how that works. So here are the various strings that we found, and for this case, they're all with area codes. Okay, how about finding names? So names can be tricky when you get Dutch and Scottish names. So for the most part, what are we going to assume a name is? A name is a capital letter followed by lowercase letters. And if we have a first name and a last name, we would expect us to have a first name, some spaces, followed by a last name. So that's the first name format. And so here I'm taking this text, which is an HTML page pulled from the University of Utah. And what we can see is there's lots of strings in the HTML page that have the same pattern that we're expecting for a name. So campus directory looks like a name, just like Rosalie McFarlane or Kaylin. Human genetics, George Kevin. So there are challenges in getting the sensitivity and specificity. Let's write a regular expression for the second format of the name, which is a last name, comma, space, first name. And so I have my last name pattern, a capital letter followed by lowercase letters, comma, 1 or more spaces, and then the same name pattern. Let's see how that looks. Okay, so we also have other things that are looking like names, colleges, comma, departments, but I am finding Chapman, comma, Brian, Chapman, comma, David, etc. Okay, so now I've defined this test string, and I also have I've put in a little FASTA file that I made. And I want you to on your own, play with writing regular expressions to find these different patterns. So find all alphanumeric strings that end in ithon, find all instances of Brian ignoring case, and these are all to be done with test string, except for use a non-greedy regular expression to find all the non-overlapping k-mers. That's in the sequence FASTA, and I provide all the code for that except for the regular expression. I have created a file called classprep.py that has my own solutions in them, so you can look at what you write versus what I wrote to get a little practice.